Right now, as you're watching this video, everything around you is moving away from everything else at speeds that would terrify you if you could perceive them directly. The galaxy containing billions of stars is racing away from neighboring galaxies at thousands of kilometers per second. Space itself is stretching, carrying matter along with it in a cosmic exodus that began 13.8 billion years ago and continues to accelerate with each passing moment. We thought the universe was static, eternal, and unchanging. We were spectacularly wrong about everything. Here's what makes this revelation deeply unsettling. The expansion of space isn't like an explosion where matter flies apart from a central point. It's something far stranger. Space itself is growing, creating new distance between objects without them actually moving through space. Imagine if the distance between your house and your neighbor's house doubled overnight, not because either building moved, but because the land itself stretched. That's what's happening on cosmic scales every second of every day. The speed of this expansion depends entirely on how far you look. Nearby galaxies recede slowly, while distant galaxies flee at velocities approaching the speed of light. The most distant observable objects are rushing away from us at over 90% light speed, not because they're moving that fast through space, but because space itself has expanded so dramatically since their light began its journey toward us. But here's the discovery that shattered every assumption about cosmic destiny. For most of human history, scientists assumed that gravity would eventually slow down the expansion, perhaps even reverse it into a cosmic collapse. In 1998, astronomers made an observation that defied every prediction. The expansion of the universe is not slowing down. It's speeding up. This cosmic acceleration is driven by something we call dark energy, a mysterious force that fills empty space and pushes everything apart with increasing strength. Dark energy comprises roughly 68% of everything that exists, yet we understand almost nothing about its nature. It's the most abundant component of reality, and it's completely invisible to our instruments, except through its effect on cosmic expansion. Tonight, we're going to unravel one of the most profound mysteries in modern science. We will discover how astronomers measure the speed of cosmic expansion across distances so vast they challenge human comprehension. We'll explore how they determined that galaxies billions of light years away are racing away from us at thousands of kilometers per second. And we'll confront the disturbing implications of a universe that's accelerating toward a cold, empty future. The story begins with a simple observation that anyone can make on a clear night. When you look up at distant galaxies through a telescope, their light appears redder than it should be. This cosmic redshift was the first clue that space itself might be expanding, carrying galaxies away from us like raisins in rising bread dough. Dr. Adam Rees, who won the Nobel Prize for discovering cosmic acceleration, described the magnitude of the revelation. We set out to measure how much the expansion was slowing down due to gravity. Instead, we discovered that some unknown force is pushing the universe apart faster and faster. It was like dropping a ball and watching it fall upward. The measurements required to determine cosmic expansion speeds push observational astronomy to its absolute limits. To measure how fast distant galaxies are moving, astronomers must detect shifts in the wavelength of light that amount to parts per million. They must account for the motion of Earth, the solar system, and our entire galaxy through space. They must calibrate their distance measurements using objects billions of times fainter than anything visible to the naked eye. These technical challenges pale compared to the conceptual implications. If the universe is expanding at an accelerating rate, what does this mean for the ultimate fate of everything? Will galaxies eventually recede so fast that they disappear beyond our observable horizon? Will space expand so rapidly that it tears apart atoms themselves? Will intelligent life survive in a universe racing toward maximum entropy? The current best measurement puts the expansion rate at approximately 70 kilometers per second per megaparsec. This means that for every 3.26 million light-years of distance, space expands fast enough to carry objects away from each other at 70 kilometers per second. At the distance of the nearest large galaxy, Andromeda, this expansion rate is negligible compared to gravitational attraction. But at cosmological distances, expansion dominates over all other forces. Recent observations have revealed something even more puzzling. Different methods for measuring the expansion rate yield slightly different answers. This Hubble tension suggests either systematic errors in our measurements or new physics beyond our current understanding. The universe might be expanding faster than our best theories predict, pointing toward revolutionary discoveries about the nature of space, time, and energy. The European Space Agency's Planck satellite measured the cosmic microwave background, the afterglow of the Big Bang, and inferred an expansion rate of 67.4 kilometers per second per megaparsec. Meanwhile, direct observations of nearby supernovae and variable stars suggest a rate of 73.2 kilometers per second per megaparsec. This 9% discrepancy might seem small, but it represents a fundamental crisis in cosmology. As we journey through the evidence for cosmic expansion, you will discover that measuring the speed of the universe requires some of the most ingenious techniques ever developed in science. Astronomers use exploding stars as cosmic lighthouses, variable stars as standard candles, and the brightness of entire galaxies as distance indicators. Each method has its own systematic uncertainties and observational challenges. If you're fascinated by the largest scale physics in the universe and want to understand how we measure cosmic distances and velocities, subscribe and hit the thumbs up button. And here's something to consider. If you could travel faster than the speed of light, could you catch up to the most distant galaxies, or would they forever remain beyond your reach due to the expansion of space itself? Comment below. I'll pin the most insightful answer. The expansion of the universe connects the smallest quantum fluctuations in the early cosmos to the largest structures we observe today. Understanding how fast space expands reveals not just where the universe is going, but where it came from and how it evolved the complex structures that make our existence possible. Now let us begin our exploration of the most ambitious measurement program in the history of science humanity's quest to determine the speed of cosmic expansion and uncover the ultimate fate of everything that exists. Chapter 1. Moving Universe. For most of human history, the universe seemed like the ultimate example of permanence and stability. The stars appeared fixed in their constellations, the planets followed predictable paths, and the cosmic architecture seemed eternal and unchanging. Even when scientists developed sophisticated models of planetary motion and stellar evolution, they assumed these changes occurred within a static cosmic framework that remained fundamentally constant across all of time. This assumption of cosmic stability was so deeply ingrained that it influenced the greatest minds in physics and astronomy. When Albert Einstein developed general relativity in 1915, his equations initially predicted that the universe should either be expanding or contracting. Rather than accept this radical implication, Einstein introduced what he called the cosmological constant, a repulsive force that would exactly balance gravity and keep the universe static. Einstein later called the cosmological constant his greatest mistake. But at the time, the assumption of a static universe seemed so obviously correct that modifying fundamental physics appeared preferable to accepting cosmic expansion. The idea that space itself could grow, stretch, and carry matter along with it was simply too alien to early 20th century thinking to be taken seriously. The first crack in this static worldview came from theoretical work by Russian mathematician Alexander Friedmann and Belgian priest Georges Lemaître in the 1920s. Working independently, both scientists found solutions to Einstein's field equations that described expanding universes. Lemaître went further, proposing that if the universe was expanding now, it must have been smaller and denser in the past, eventually reaching a state of infinite density at some finite time ago. Lemaitre's proposal, which he called the hypothesis of the primeval atom, suggested that the entire observable universe had emerged from an initial state of unimaginable compression and heat. This idea seemed so outlandish that many astronomers, including Einstein himself, initially rejected it as mathematically interesting but physically meaningless. The resistance to these theoretical predictions stemmed partly from philosophical objections to the idea of a universe with a beginning. The concept of cosmic genesis implied questions about what existed before the beginning and what caused the initial expansion. Many scientists preferred models of an eternal, steady-state universe that avoided these metaphysically troubling questions. But nature doesn't care about human philosophical preferences, and observations were beginning to reveal hints that the universe might indeed be far more dynamic than anyone had imagined. The key breakthrough came from studying the light from distant galaxies and discovering that this light carried unmistakable signatures of cosmic motion. During the 1910s and 1920s, astronomers using large telescopes began making systematic observations of spiral nebulae fuzzy patches of light that we now know are entire galaxies containing billions of stars. These observations required photographic plates with exposure times of many hours, since the galaxies were so faint that their light could barely be detected even with the largest telescopes available. Vesto Slipher, working at Lowell Observatory in Arizona, made meticulous measurements of the spectra of these spiral nebulae. Spectroscopy, the technique of spreading light into its component colors, revealed that nearly all of these distant objects showed systematic shifts in their spectral lines toward longer, redder wavelengths. This redshift phenomenon was well understood from laboratory physics and terrestrial astronomy. When a light source moves away from an observer, the Doppler effect stretches the wavelengths of the light, shifting them toward the red end of the spectrum. The faster the recession velocity, the greater the redshift. Slipher's observations suggested that almost all spiral nebulae were rushing away from the Milky Way at speeds of hundreds or even thousands of kilometers per second. Dr. Vera Rubin, who made fundamental contributions to understanding galactic motions, described the significance of these early observations. Slipher's measurements revealed that we live in a universe where almost everything is moving away from us. This couldn't be a coincidence. It pointed towards something fundamental about the structure of space and time. The pattern Slipher discovered was unlike anything seen in terrestrial or solar system astronomy. In our local cosmic environment, objects move in various directions with no preferred pattern. Stars orbit the galactic center, planets orbit stars, and galaxies within clusters can move toward or away from each other depending on their gravitational interactions. But the spiral nebulae showed a clear systematic pattern. The vast majority were redshifted, indicating recession. Even more puzzling, the recession velocities were enormous compared to typical astronomical motions. The fastest moving stars in our galaxy rarely exceed a few hundred kilometers per second, while Slipher was measuring recession velocities of over 1,000 kilometers per second for some spiral nebulae. These speeds were so extreme that they challenged understanding of what could accelerate such massive objects to such velocities. The interpretation of these observations was initially uncertain. Were the spiral nebulae relatively small, nearby objects being ejected from our galaxy at high speeds? Were they distant island universes, entire galaxies comparable to our own Milky Way? If they were truly distant, what force could be driving them away from us at such tremendous velocities? The distance question was resolved through the pioneering work of Edwin Hubble and his colleagues at Mount Wilson Observatory in California. Using the 100-inch telescope, then the largest in the world, Hubble identified individual variable stars in nearby spiral nebulae. These Cepheid variable stars had a known relationship between their brightness and their pulsation period, making them excellent distance indicators. Hubble's distance measurements revealed that spiral nebulae were indeed distant galaxies, located millions of light-years away rather than within our own galactic neighborhood. This discovery immediately transformed the scale of the known universe and confirmed that we live in a cosmos populated by countless galaxy clusters separated by vast reaches of empty space. But combining Hubble's distance measurements with Slipher's velocity measurements revealed something even more extraordinary. There was a clear relationship between distance and recession velocity. The more distant the galaxy, the faster it was moving away from us. This wasn't the pattern you would expect if galaxies were simply flying apart from some central explosion. Instead, it suggested something far more profound about the nature of space itself. The relationship between distance and recession velocity, now known as Hubble's law, implied that space everywhere was expanding uniformly. Rather than galaxies moving through static space, space itself was growing, carrying galaxies along with it like raisins in rising bread dough. This expansion would naturally produce the observed correlation between distance and velocity without requiring any special position for our galaxy. Computer simulations of expanding space confirmed this interpretation. In an expanding universe, every observer would see the same pattern. Distant objects receding faster than nearby ones, with recession velocity proportional to distance. The pattern had nothing to do with our special location and everything to do with the fundamental properties of expanding spacetime. The implications were staggering. If space was expanding now, extrapolating backward in time suggested that the universe had been much smaller and denser in the past. Following this logic to its conclusion implied a cosmic beginning when all matter and energy were compressed into an infinitely dense state. The scenario Lemaître had proposed based purely on theoretical considerations. Dr. Steven Weinberg, Nobel laureate and cosmology pioneer, captured the revolutionary nature of this discovery. The expanding universe gave us our first glimpse of cosmic evolution. Instead of an eternal, unchanging cosmos, we discovered a dynamic universe with a history, a present, and a future. The discovery of cosmic expansion fundamentally changed humanity's perspective on our place in the universe. We were no longer inhabitants of a static eternal cosmos, but participants in an evolving cosmic story that began with a moment of creation and would continue evolving into an uncertain future. Yet these early measurements only scratched the surface of cosmic expansion. The true complexity and mystery of universal expansion would only become apparent as observational techniques improved and astronomers began to probe deeper into space and further back in cosmic time. Chapter 2. Cosmic Scale. Understanding the speed of cosmic expansion requires grappling with distances so vast that human intuition completely fails to comprehend them. When astronomers measure the expansion rate of the universe, they're determining how fast space itself grows across scales that dwarf everything in human experience. To appreciate what cosmic expansion actually means, we need to understand the mind-bending scales over which it operates. The fundamental unit astronomers use to measure cosmic expansion is the megaparsec, roughly 3.26 million light-years, or about 31 trillion kilometers. To put this in perspective, a single megaparsec is approximately the distance to the Andromeda Galaxy, our nearest large galactic neighbor. Light traveling from Andromeda takes over 2.5 million years to reach Earth, crossing a distance so vast that if you could travel there at the speed of a commercial airliner, the journey would take over 3 billion years. But a single megaparsec represents just the beginning of cosmic distance scales. The observable universe extends roughly 14,000 megaparsecs in every direction, encompassing a sphere with a diameter of nearly 93 billion light-years. Within this cosmic volume, astronomers can observe galaxies at distances where the expansion of space carries them away from us at velocities approaching the speed of light. Dr. Wendy Friedman, who led major efforts to measure cosmic expansion, describe the challenge of cosmic scales. When we talk about measuring the expansion rate of the universe, we're trying to determine how fast space grows across distances larger than anything humans can directly experience. It's just like trying to measure the rate at which the ocean grows while standing on a beach. The current best measurement of cosmic expansion rate, known as the Hubble constant, is approximately 70 kilometers per second per megaparsec. This seemingly simple number contains profound implications for our understanding of cosmic dynamics. It means that for every megaparsec of distance between two points in space, the expansion of the universe causes them to separate at 70 kilometers per second. Consider what this means for galaxies at different distances. A galaxy located 10 megaparsecs away recedes at 700 kilometers per second due to cosmic expansion. A galaxy at 100 megaparsecs recedes at 7,000 kilometers per second. A galaxy at 1,000 megaparsecs, still well within the observable universe, recedes at 70,000 kilometers per second, or about 23% the speed of light. At these recession velocities, the effects of cosmic expansion become dramatic and counterintuitive. Light emitted from distant galaxies is severely redshifted by the time it reaches us, not because the galaxies are moving rapidly through space, but because space itself has expanded during the light's journey. The most distant observable galaxies have redshifts so large that their ultraviolet light reaches us shifted all the way into the infrared spectrum. The expansion rate also determines fundamental properties of the observable universe. The Hubble constant sets the scale for what astronomers call the Hubble distance, roughly 14 billion light-years beyond which objects recede faster than the speed of light due to expansion. This doesn't violate relativity because the objects aren't moving through space faster than light. Rather, space itself is expanding fast enough to create recession velocities exceeding light speed. This cosmic horizon creates a boundary to our observable universe that has nothing to do with the finite age of the cosmos or the travel time of light. Even if we wait billions of years, we will never receive light from objects currently beyond the Hubble distance because space expands faster than light can traverse it. In effect, cosmic expansion creates regions of the universe that are permanently inaccessible to our observation. The measurement of cosmic expansion requires determining both distances and recession velocities across these vast scales. Velocity measurements come from spectroscopy analyzing how cosmic expansion redshifts the light from distant objects. But distance measurements require a sophisticated chain of calibrated standard candles and standard rulers that astronomers have spent decades developing and refining. The closest link in this cosmic distance ladder uses parallax measurements of nearby stars. As Earth orbits the Sun, nearby stars appear to shift slightly against the background of more distant stars. These parallax shifts, typically measured in thousandths of an arcsecond, provide direct geometric distance measurements to stars within a few thousand light-years of Earth. Parallax measurements calibrate the distances to Cepheid variable stars' pulsating giants, whose intrinsic brightness correlates with their pulsation period. Once this correlation is calibrated using nearby Cepheids with known parallax distances, astronomers can use more distant Cepheids as standard candles to measure distances to nearby galaxies. The European Space Agency's Gaia mission has revolutionized parallax astronomy by measuring the positions and motions of over 1 billion stars with unprecedented precision. These measurements provide the foundation for the entire cosmic distance scale, extending our reach from the solar neighborhood to the edge of the observable universe. Beyond the reach of Cepheid variables, astronomers use Type Ia supernovae as standard candles for measuring distances to galaxies billions of light-years away. These stellar explosions reach peak brightnesses that are remarkably consistent, allowing them to be calibrated as cosmic lighthouses visible across vast distances. The combination of supernova brightness and redshift measurements provides direct evidence for cosmic Expansion at the largest observable scales. Recent observations have extended these measurements to redshifts where we observe galaxies as they appeared when the universe was less than 10% of its current age. At these distances, cosmic expansion becomes so significant that space has nearly doubled in size. During the light travel time from these galaxies to Earth, the cosmic microwave background, the afterglow radiation, from the early universe provides another crucial probe of expansion history. This radiation, detected uniformly across the sky, carries imprints of density fluctuations that existed when the universe was only 380,000 years old. The angular scale of these fluctuations depends on the expansion history of the universe, providing an independent measurement of the Hubble constant. Dr. Planck collaboration S analysis of cosmic microwave background data yielded a Hubble constant of 67.4 kilometers per second per megaparsec, with uncertainties of less than 1%. This represents one of the most precise cosmological measurements ever achieved, based on observations of the universe when it was less than 0.003% of its current age. However, this value disagrees with direct measurements using the cosmic distance ladder, which consistently yield higher values around 73 to 74 kilometers per second per megaparsec. This Hubble tension represents one of the most significant challenges in modern cosmology, suggesting either unknown systematic errors or new physics beyond our current understanding. The implications of this tension extend far beyond technical concerns about measurement accuracy. If the disagreement reflects real physics rather than measurement errors, it could indicate that our understanding of cosmic expansion is fundamentally incomplete. New forms of matter or energy, modifications to gravity, or exotic physics in the early universe might be required to reconcile these observations. The scale of cosmic expansion also raises profound questions about the ultimate structure and fate of the universe. If expansion continues indefinitely, will distant galaxies eventually recede so fast that they disappear beyond our cosmic horizon? Will the expansion rate continue to accelerate, or might it change over cosmic timescales? Future surveys will measure cosmic expansion with unprecedented precision across cosmic history. The Vera-Rubin Observatory will discover millions of supernovae, extending Type Ia measurements to higher redshifts and greater statistical precision. The Euclid space mission will map the positions and redshifts of billions of galaxies, providing three-dimensional maps of cosmic structure evolution. These observations will test whether the expansion rate has remained constant over cosmic time or has evolved in response to changing cosmic conditions. They may reveal new physics operating on the largest scales in the universe, or confirm that our current understanding of cosmic expansion captures the essential physics of space-time dynamics. The measurement of cosmic expansion represents humanity's most ambitious attempt to understand the dynamics of the entire observable universe. From parallax measurements of nearby stars to observations of galaxies billions of light years away, this enterprise connects the smallest measurable motions to the largest scale phenomena in nature, revealing the fundamental rate at which space itself grows and evolves. Chapter 3. Redshift. The key to measuring cosmic expansion lies in a phenomenon that transforms the very nature of light as it travels across the vast expanses of the universe. When astronomers observe distant galaxies, they discover that the light reaching us has been fundamentally altered during its journey through expanding space. This cosmic redshift serves as both a speedometer and a clock, revealing not only how fast objects are receding from us, but also how much the universe has expanded since the light began its journey. The physics of redshift begins with understanding light as electromagnetic waves characterized by specific wavelengths and frequencies. When a light source moves away from an observer, the Doppler effect stretches these wavelengths, shifting them toward the red end of the electromagnetic spectrum. This phenomenon is familiar from everyday experience. the changing pitch of an ambulance siren as it approaches and recedes. But cosmic redshift reveals effects far more dramatic than anything encountered in terrestrial physics. For galaxies in the nearby universe, redshift operates much like the familiar Doppler effect. If a galaxy moves away from us at 3,000 kilometers per second, about 1% the speed of light, its light is redshifted by approximately 1%. Spectral lines that appear at specific wavelengths in laboratory measurements are shifted to slightly longer wavelengths when observed from the receding galaxy. This may seem like a small effect, but modern spectrographs can measure wavelength shifts with extraordinary precision. The most advanced instruments can detect redshift changes as small as 1 part in 100 million, equivalent to measuring velocities as low as 3 meters per second. This precision allows astronomers to detect the gravitational wobble of stars caused by orbiting planets, demonstrating the remarkable sensitivity of redshift measurements. Dr. Saul Perlmutter, who shared the Nobel Prize for discovering cosmic acceleration, described the power of redshift observations. When we measure the redshift of distant galaxies, we're not just determining how fast they're moving away from us. We're measuring how much space itself has grown since the light left those galaxies. It's like having a cosmic tape measure that stretches with the universe. But for the most distant galaxies, redshift reveals effects that go far beyond simple Doppler motion. At cosmological distances, the redshift is caused not by galaxies moving through space, but by the expansion of space itself during the light's journey. This cosmological redshift can produce shifts far larger than anything possible through conventional Doppler effects. Consider light from a galaxy so distant that it has taken 10 billion years to reach us. During this light travel time, the universe has expanded significantly, stretching the wavelengths of all photons traveling through space. By the time this ancient light reaches our telescopes, it may have been redshifted by factors of 2, 3, or even more, meaning space has doubled or tripled in size since the light began its journey. The most distant galaxies observable with current telescopes have redshifts exceeding z equals 10, where z represents the fractional increase in wavelength. A redshift of z equals 10 means that wavelengths have been stretched by a factor of 11, indicating that the universe is 11 times larger now than when that light was emitted. These galaxies appear as they were when the universe was less than 500 million years old, less than 4% of its current age. At such extreme redshifts, ultraviolet light emitted by hot young stars is shifted all the way into the infrared spectrum by the time it reaches Earth. This is why space-based infrared telescopes like the Hubble Space Telescope and James Webb Space Telescope are crucial for studying the most distant parts of the universe. What appears as infrared radiation to our instruments was originally high-energy ultraviolet light from some of the first stars and galaxies to form in cosmic history. The measurement of cosmic redshift requires sophisticated spectroscopic techniques that can identify specific atomic and molecular transitions in the light from distant objects. Hydrogen, the most abundant element in the universe, produces characteristic spectral lines at well-known wavelengths. When astronomers observe these lines in galaxy spectra, they can measure precisely how much the wavelengths have been stretched by cosmic expansion. The Lyman alpha line of hydrogen, which appears at 121.6 nanometers in laboratory measurements, serves as one of the most important redshift indicators for distant galaxies. In a galaxy with redshift z equals 6, this line appears at 851 nanometers, shifted from the ultraviolet into the near-infrared spectrum. The precise measurement of this wavelength shift reveals both the galaxy's distance and the expansion rate of the universe. Multi-object spectrographs on large telescopes can simultaneously measure redshifts for hundreds of galaxies in a single observation, creating three-dimensional maps of cosmic structure across billions of light-years. These surveys reveal the large-scale distribution of matter in the universe and how this distribution has evolved as cosmic expansion has proceeded. The Sloan Digital Sky Survey, one of the most ambitious astronomical projects ever undertaken, has measured redshifts for over 3 million galaxies and quasars. This massive dataset reveals the cosmic web, a complex network of filaments and voids that represents the largest scale structure in the universe. The redshift measurements show how this structure has evolved over cosmic time as expansion has stretched the underlying pattern of matter distribution. But redshift measurements also reveal puzzling discrepancies that challenge our understanding of cosmic expansion. Different methods for measuring the same galaxy's redshift can yield slightly different results, particularly for very distant objects where the measurements approach the limits of instrumental precision. These systematic effects must be carefully understood and corrected to obtain accurate expansion rate measurements. The interpretation of redshift becomes more complex when considering the effects of peculiar velocities, the individual motions of galaxies through space, in addition to the expansion-driven recession. Galaxies move under the gravitational influence of nearby matter concentrations, creating additional Doppler shifts that must be separated from the cosmological redshift to determine the pure expansion effect. For nearby galaxies, these peculiar velocities can be substantial. Our local group of galaxies is falling toward the Virgo cluster at about 200 kilometers per second, while the entire local supercluster appears to be streaming toward an even more distant mass concentration called the Great Attractor. These complex motions create variations in observed redshift that must be modeled and corrected in precision expansion measurements. Recent observations have also revealed that redshift itself may evolve over cosmic time in ways that reflect changing expansion rates. If the universe's expansion has been accelerating, as observations suggest, then the relationship between redshift and distance should differ for galaxies at different cosmic epochs. Measuring these subtle effects requires extraordinary precision in both redshift and distance determinations. The James Webb Space Telescope has begun pushing redshift measurements to unprecedented distances, potentially observing galaxies from when the universe was less than 200 million years old. These observations probe cosmic expansion during the epoch when the first stars and galaxies were forming, providing tests of cosmological models during the universe's youth. Gravitational lensing by massive galaxy clusters can magnify the light from extremely distant background galaxies, making them bright enough for detailed redshift measurements. This technique has revealed galaxies at redshifts exceeding Z equals 11. Showing cosmic expansion during the first few 100 million years after the Big Bang. The future of redshift astronomy includes surveys that will measure precise redshifts for billions of galaxies across cosmic history. The Dark Energy Survey, Large Synoptic Survey Telescope, and Euclid mission will create 4-dimensional maps of the universe, 3 spatial dimensions plus cosmic time, revealing how expansion has proceeded across 13 billion years of cosmic evolution. These surveys may reveal whether cosmic expansion is truly uniform across all directions and scales, or whether there are subtle variations that point toward new physics. They will test whether the redshift-distance relationship has remained constant over cosmic time, or whether it has evolved in response to changing cosmic conditions. Understanding cosmic redshift has transformed from a curiosity about distant galaxy colors into one of humanity's most powerful tools for probing the fundamental nature of space and time. Each redshift measurement provides a direct probe of cosmic expansion, revealing how the universe has grown and evolved since ancient light began its journey across the cosmos. Chapter 4: Hubble's discovery in the late 1920s. A quiet, meticulous astronomer working at Mount Wilson Observatory made observations that would forever change humanity's understanding of the cosmos. Edwin Hubble, using what was then the world's largest telescope, discovered that the universe was not static and eternal as everyone believed, but expanding at a rate that increased with distance. This discovery, made through painstaking measurements of faint galaxies, revealed that we live in a dynamic, evolving universe with a definite beginning and an uncertain future. Hubble's path to this cosmic revelation began with resolving one of astronomy's greatest debates: the nature of spiral nebulae. These fuzzy patches of light visible through telescopes had puzzled astronomers for decades. Were they relatively nearby clouds of gas within our own galaxy? Or were they distant island universes comparable to the Milky Way itself? The answer would determine whether our galaxy represented the entire universe or just one among countless others. The key breakthrough came from Hubble's identification of Cepheid variable stars in the Andromeda Nebula. These pulsating giants brighten and dim with periods that correlate precisely with their intrinsic luminosity. The longer the period, the brighter the star. Henrietta Swan Leavitt had discovered this period luminosity relationship while studying Cepheids in the Magellanic Clouds, providing astronomers with their first reliable standard candle for cosmic distance measurements. Working with the 100-inch Hooker telescope, Hubble spent countless nights photographing individual regions of Andromeda, searching for stars that varied in brightness over timescales of days to weeks. The work was exhausting and technically demanding, requiring photographic exposures of many hours and precise measurements of stellar brightnesses from the developed plates. When Hubble finally identified Cepheid variables in Andromeda and applied Leavitt's period luminosity relationship, the results were shocking. The distance to Andromeda was approximately 900,000 light-years far beyond the boundaries of our own galaxy. This single measurement proved that spiral nebulae were indeed distant galaxies, instantly expanding the known universe by factors of thousands. Dr. Alan Sandage, who worked closely with Hubble and continued his research for decades, described the magnitude of this discovery. Hubble didn't just find that the universe was larger than we thought. He showed that our galaxy was just one among billions scattered across a cosmos of almost unimaginable scale. It was like discovering that your hometown was actually just one house among millions in a vast city. But Hubble's most revolutionary discovery was yet to come. Combining his distance measurements with Vesto Slipher's earlier redshift observations, Hubble found a remarkable relationship. The more distant a galaxy, the faster it was receding from us. This wasn't the random pattern you would expect from galaxies moving independently through space. Instead, it suggested a systematic expansion of space itself. The relationship, now known as Hubble's law, could be expressed with elegant simplicity. Recession velocity equals distance multiplied by a constant. This Hubble constant, initially estimated at about 500 kilometers per second per megaparsec, described the rate at which the universe was expanding. Every megaparsec of distance corresponded to an additional 500 kilometers per second of recession velocity. Hubble's initial distance scale was incorrect by a large factor, leading to an overestimate of the expansion rate and an uncomfortably young age for the universe. But the fundamental relationship he discovered was sound. Distant objects recede faster than nearby ones, with recession velocity proportional to distance. This was exactly what would be expected in an expanding universe where space itself grows uniformly. The implications were staggering and controversial. If the universe was expanding now, extrapolating backward in time suggested that everything had been compressed into an extremely dense state in the past. Belgian physicist Georges Lemaître calculated that this primeval atom would have existed roughly 2 billion years ago, a cosmic beginning that challenged prevailing assumptions about eternal, static cosmos. Many astronomers, including Hubble himself, were reluctant to accept the full implications of the expansion discovery. Alternative explanations were proposed. Perhaps light somehow tired during its journey across vast distances, creating an apparent redshift without actual recession. Perhaps the laws of physics operated differently on cosmic scales, creating systematic effects that mimicked expansion. These alternative explanations were eventually ruled out by more detailed observations and theoretical analysis. Tired light models predicted specific changes in the spectral properties of distant galaxies that weren't observed. Steady-state cosmologies required continuous creation of matter to maintain constant density in an expanding universe, a process for which no evidence could be found. The expansion discovery also resolved a long-standing puzzle known as Olber's paradox. If the universe were infinite, eternal, and uniformly filled with stars, the night sky should be as bright as the surface of the sun, since every line of sight would eventually intersect a stellar surface. The darkness of night suggested that either the universe was finite in age or size, or that its properties changed over cosmic timescales. An expanding universe that began at a finite time naturally explained Olber's paradox. The night sky is dark because the universe has a finite age, and light from the most distant stars hasn't had time to reach us yet. Moreover, cosmic expansion redshifts light from distant sources, reducing their apparent brightness and contributing to the darkness of space. Hubble's observations required extraordinary technical precision for their era. Measuring the tiny brightness variations of Cepheid variables in distant galaxies pushed photographic techniques to their limits. Hubble had to account for atmospheric effects, instrumental systematics, and the challenge of detecting faint stars against bright galactic backgrounds. The redshift measurements were equally demanding. Spectroscopic observations required long exposures with large telescopes to collect enough light for analysis. The wavelength shifts being measured were often less than 1% of the original wavelengths, requiring careful calibration and stability in the spectrographic instruments. Despite these technical challenges, Hubble's initial sample included only 24 galaxies with reliable distance and velocity measurements. This small dataset was sufficient to establish the distance-velocity relationship, but left considerable uncertainty in the exact value of the expansion rate and its interpretation. Subsequent observations expanded and refined Hubble's initial results. Milton Humason, working with Hubble at Mount Wilson, extended redshift measurements to much more distant galaxies, finding recession velocities exceeding 40,000 kilometers per second. These extreme velocities, representing more than 10% the speed of light, provided compelling evidence that the expansion relationship extended to the largest observable scales. The period following Hubble's discovery saw intense theoretical development as cosmologists worked to understand the implications of an expanding universe. Alexander Friedmann's solutions to Einstein's field equations provided mathematical frameworks for describing cosmic expansion, while observational cosmology developed techniques for measuring expansion rates and testing cosmological models. World War II interrupted astronomical research, but post-war technological developments revolutionized observational capabilities. New telescopes, improved photographic emulsions, and electronic detectors allowed astronomers to extend Hubble's work to much greater distances and higher precision. Walter Baades' discovery that there were two distinct populations of Cepheid variables led to a major revision of the cosmic distance scale in the 1950s. This correction reduced Hubble's constant by approximately a factor of 2. Resolving discrepancies between the apparent age of the universe and the ages of the oldest stars. Throughout the latter half of the 20th century, successive generations of astronomers refined measurements of the Hubble constant using improved distance indicators and larger telescopes. Each improvement revealed new complexities in cosmic expansion while confirming the basic relationship Hubble had discovered. The Hubble Space Telescope, named in honor of the expansion discoverer, has provided the most precise measurements of cosmic distances and expansion rates. Free from atmospheric distortions, space-based observations can detect Cepheid variables in galaxies hundreds of times more distant than those accessible to Hubble's ground-based observations. Modern measurements place the Hubble constant at approximately 70 kilometers per second per megaparsec, much lower than Hubble's initial estimate, but confirming the systematic relationship he discovered. This value implies that the observable universe is roughly 13.8 billion years old, consistent with independent age measurements from stellar evolution and nuclear physics. Hubble's discovery of cosmic expansion ranks among the greatest scientific achievements of the 20th century, comparable to Darwin's theory of evolution or Einstein's relativity. It transformed our understanding of cosmic architecture and revealed that we live in a dynamic, evolving universe whose properties change dramatically over time. Chapter 5. Standard candles measuring cosmic expansion requires determining both the distances and recession velocities of galaxies across the observable universe. While redshift measurements provide velocities relatively easily, measuring cosmic distances presents one of the most challenging problems in astronomy. The solution lies in identifying standard candles, astronomical objects with known intrinsic brightness that can serve as cosmic lighthouses, allowing astronomers to calculate distances by comparing apparent brightness to absolute luminosity. The concept of standard candles is elegantly simple in principle, but extraordinarily difficult to implement in practice. If you know how bright an object actually is and can measure how bright it appears from Earth, you can calculate its distance using the inverse square law of brightness. Light spreads out as it travels, becoming dimmer by the square of the distance. An object 4 times farther away appears 16 times fainter, while an object 10 times farther away appears 100 times fainter. The challenge lies in finding astronomical objects whose intrinsic brightness can be determined reliably. Stars come in an enormous range of luminosities, from red dwarfs, thousands of times fainter than the Sun, to hypergiants millions of times brighter. Without knowing which type of star you're observing, brightness measurements reveal nothing about distance. The breakthrough came from studying variable stars objects whose brightness changes periodically over timescales ranging from hours to years. These variations often result from physical pulsations in the star's outer layers, and the pulsation period depends on the star's internal structure, which is closely related to its mass and luminosity. Cepheid variable stars provided the first reliable standard candles for extragalactic astronomy. These yellow supergiant stars pulsate with periods ranging from a few days to several months, changing brightness by factors of 2 to 10 during each cycle. Henrietta Swan Leavitt's discovery of the period luminosity relationship for Cepheids in the Magellanic Clouds established that longer period Cepheids are intrinsically brighter than shorter period ones. Dr. Wendy Friedman, who led the Hubble Space Telescope Key project to measure the Hubble constant, described the importance of Cepheids. These stars are like cosmic lighthouses with calibrated brightness. Once we understand the relationship between their pulsation periods and their intrinsic luminosity, we can use them to measure distances anywhere we can detect them in the universe. Calibrating the Cepheid period luminosity relationship required determining accurate distances to nearby Cepheids using geometric methods. Parallax measurements, detecting the tiny apparent shifts in stellar positions as Earth orbits the Sun, provide direct distance measurements to stars within a few thousand light years. The European Space Agency's Gaia mission has revolutionized this field, measuring parallax distances to Cepheids with unprecedented precision. With proper calibration, Cepheids can provide distance measurements accurate to about 5% for galaxies within roughly 100 million light-years. The Hubble Space Telescope, a sharp resolution, allows detection of individual Cepheids in galaxies far beyond the reach of ground-based telescopes, extending the cosmic distance ladder to significant fractions of the observable universe. But even Cepheids have limitations. At distances beyond about 30 megaparsecs, individual Cepheids become too faint to detect reliably even with space telescopes. Measuring cosmic expansion to the largest scales requires even brighter standard candles that remain visible across billions of light years. The solution came from studying stellar explosions known as Type Ia supernova. These catastrophic events occur when white dwarf stars, the dense remnants of solar mass stars, accrete material from companion stars and exceed a critical mass threshold. The white dwarf undergoes thermonuclear explosion, briefly outshining entire galaxies and becoming visible across cosmological distances. Type Ia supernova serve as excellent standard candles because the explosion mechanism produces remarkably consistent peak luminosities. The critical mass for a white dwarf explosion, approximately 1.4 solar masses, is set by fundamental physics, leading to similar energy releases and peak brightnesses for these events. Small variations in peak luminosity correlate with measurable properties like light curve shape and spectral features, allowing astronomers to calibrate individual supernova brightnesses. The discovery that Type Ia supernova could serve as precise cosmic distance indicators revolutionized observational cosmology. These stellar explosions are roughly 5 billion times brighter than the Sun at peak luminosity, making them detectable in galaxies billions of light years away. Unlike Cepheids, which require careful observation of individual stars, supernova announce their presence with unmistakable brightening that can be detected by automated survey telescopes. Dr. Saul Perlmutter, who led one of the teams that discovered cosmic acceleration using supernova, explained their unique value. Type Ia supernova are like billion-watt light bulbs going off throughout the universe. They're bright enough to see across cosmic time and consistent enough to measure tiny distance differences that reveal how expansion has changed over billions of years. Building a reliable sample of supernova distances requires systematic surveys that can discover these events soon after explosion and follow their light curves over several months. The Supernova Cosmology Project and High-Z Supernova Search team pioneered techniques for finding and studying distant supernova, ultimately discovering over 100 Type Ia events at redshifts where the universe was significantly younger than today. The supernova observations revealed an unexpected and revolutionary result. Instead of finding that cosmic expansion was slowing down due to gravitational deceleration, the teams discovered that expansion was actually accelerating. Distant supernova appeared fainter than expected in a decelerating universe, indicating that space was expanding faster now than in the past. This discovery of cosmic acceleration earned the 2011 Nobel Prize in Physics and fundamentally changed our understanding of the universe's composition and fate. The acceleration implies that some form of dark energy comprising roughly 68% of the universe's energy density is driving space to expand at an increasing rate. But supernova have revealed additional complexities in cosmic expansion measurements. Different subsets of Type Ia events show slight systematic differences in their distance luminosity relationships, suggesting that the explosion mechanism may not be perfectly uniform. Environmental effects, dust extinction, and gravitational lensing can introduce systematic errors that must be carefully modeled. Recent surveys have discovered thousands of Type Ia supernova across a wide range of redshifts, from the local universe to epochs when it was less than half its current age. These large samples allow detailed studies of systematic effects and provide increasingly precise measurements of cosmic expansion history. The Pantheon supernova sample, compiled from multiple surveys, includes over 1,000 Type Ia events with high-quality light curves and host galaxy information. Analysis of this dataset provides measurements of cosmic expansion parameters with uncertainties below 2%, representing some of the most precise cosmological measurements ever achieved. Future surveys will discover tens of thousands of additional supernova, extending measurements to higher redshifts and better statistical precision. The Vera Rubin Observatory will begin operation soon, potentially discovering 100,000 Type Ia supernova over its 10-year survey lifetime. This massive dataset will probe cosmic expansion with unprecedented detail across most of cosmic history. Advanced analysis techniques are also improving the precision of supernova distance measurements. Machine learning algorithms can identify subtle correlations between supernova properties and their luminosities, potentially reducing systematic uncertainties. Three-dimensional models of explosion physics may explain the origin of luminosity variations and enable more precise standardization. Other types of standard candles are being developed to complement and cross-check supernova measurements. Surface brightness fluctuations in elliptical galaxies, gravitational lensing time delays, and tip of the red giant branch stars all provide independent distance indicators for cosmic expansion studies. The cosmic distance ladder built from these various standard candles represents one of humanity's greatest intellectual achievements. A chain of calibrated measurements extending from the solar neighborhood to the edge of the observable universe. Each link in this ladder has been refined through decades of careful observation and analysis, ultimately enabling precise measurements of how fast space itself expands across cosmic time. These distance measurements form the observational foundation for our understanding of cosmic evolution, revealing not just how fast the universe expands today, but how that expansion rate has changed over billions of years of cosmic history. Chapter 6. Acceleration Shock. In 1998, two independent teams of astronomers made an observation that shattered every assumption about cosmic destiny. They had set out to measure how much gravity was slowing down the universe's expansion, expecting to determine whether the cosmos would eventually collapse in a big crunch or expand forever at a gradually decreasing rate. Instead, they discovered something that defied all theoretical predictions. The expansion of the universe was not slowing down, it was speeding up. The Supernova Cosmology Project, led by Saul Perlmutter, and the HiZ Supernova Search Team, led by Brian Schmidt and Adam Rees, had spent years developing techniques for finding and studying Type Ia supernova in distant galaxies. Their goal was to use these stellar explosions as cosmic lighthouses to map the expansion history of the universe across billions of years of cosmic time. The theoretical expectation was straightforward. Gravity should act as a cosmic brake, gradually slowing the expansion rate over time. Depending on the total amount of matter in the universe, expansion would either slow to a halt and reverse into collapse, or continue forever, but at an ever-decreasing rate. Either way, the expansion should be decelerating due to the mutual gravitational attraction of all matter in the universe. Dr. Adam Rees, who shared the Nobel Prize for this discovery, described the moment of realization. We were expecting to measure the cosmic deceleration and determine the ultimate fate of the universe. Instead, we found that distant supernovae were fainter than expected in a decelerating universe. At first, we thought we had made a mistake, but the data kept pointing toward the same impossible conclusion. The universe is accelerating. Evidence came from comparing the apparent brightness of distant Type Ia supernova with their predicted brightness based on their redshifts and the assumption of cosmic deceleration. In a universe slowing down due to gravity, distant supernovae should appear brighter than their redshifts alone would suggest, because space would have expanded less during the light travel time than in a universe with constant expansion. Instead, the observations showed the opposite pattern. Distant supernovae appeared dimmer than expected, as if they were farther away than their redshifts indicated in a decelerating universe. This could only happen if the universe had actually expanded more during the light travel time. In other words, if cosmic expansion was accelerating rather than decelerating. The teams meticulously checked their observations for systematic errors. Perhaps dust in distant galaxies was dimming the supernova, making them appear farther away. Perhaps the stellar explosions themselves were different in the distant universe, producing intrinsically fainter events. Perhaps gravitational lensing or other relativistic effects were affecting the light paths. Every alternative explanation was systematically ruled out. Dust extinction would redden as well as dim the supernova, but the observed colors were consistent with unreddened explosions. Spectroscopic observations showed that distant supernova had the same explosion characteristics as nearby ones. Gravitational lensing effects were too small to explain the observed brightness differences. The conclusion was inescapable. Cosmic expansion was accelerating, driven by some unknown force that acted opposite to gravity on large scales. This force, quickly dubbed dark energy, appeared to comprise roughly 68% of the universe's total energy density, making it the dominant component of cosmic reality. The discovery of cosmic acceleration represented one of the most profound surprises in the history of science. Unlike many scientific breakthroughs that confirm theoretical predictions, this observation revealed a completely unexpected phenomenon that challenged fundamental assumptions about cosmic evolution and the nature of space and time. Dr. Michael Turner, who coined the term dark energy, captured the magnitude of the surprise. The discovery of cosmic acceleration was like expecting your car to slow down when you take your foot off the gas, only to find that it speeds up instead. It tells us that 68% of the universe consists of something we do not understand at all. The implications extended far beyond cosmology. If most of the universe consists of dark energy, our understanding of fundamental physics was profoundly incomplete. No known force or field predicted by the standard model of particle physics could account for the properties required of dark energy: negative pressure, near constant density as space expands, and the ability to dominate cosmic dynamics on the largest scales. The acceleration discovery also revolutionized predictions about cosmic destiny. In a universe dominated by dark energy, expansion would continue indefinitely and accelerate without limit. Eventually, distant galaxies would recede so fast that they would disappear beyond our cosmic horizon. Stars would burn out, galaxies would separate, and the universe would evolve toward a cold, empty future fundamentally different from the cyclic or steady-state cosmologies previously considered. Follow-up observations quickly confirmed and refined the acceleration discovery. Independent supernova surveys found consistent results, while observations of cosmic microwave background fluctuations and large-scale structure provided complementary evidence for dark energy. The convergence of multiple independent measurement techniques established cosmic acceleration as one of the most robust findings in observational cosmology. The Cosmic Background Explorer and Wilkinson Microwave Anisotropy probe satellites measured precise angular patterns in the cosmic microwave background radiation, revealing that the universe has flat geometry consistent with a dark energy-dominated cosmos. These observations provided completely independent confirmation of cosmic acceleration using physics of the early universe rather than stellar explosions. Large-scale structure surveys mapping the positions of millions of galaxies found that the pattern of cosmic clustering matched predictions for a universe with approximately 30% matter and 70% dark energy. The growth rate of cosmic structure depends sensitively on cosmic expansion history, providing another independent probe of acceleration. The Planck satellite's measurements of cosmic microwave background fluctuations achieved unprecedented precision, determining that dark energy comprises 68.3% of the universe's energy density with uncertainties below 1%. Combined with supernova and large-scale structure data, these observations established the concordance model of cosmology with extraordinary statistical confidence. But the nature of dark energy remains one of physics' deepest mysteries. The simplest possibility is that dark energy represents Einstein's cosmological constant, a fundamental property of empty space that creates repulsive gravity. However, Theoretical calculations predict that quantum fluctuations should create a cosmological constant trillions of times larger than observed, creating what physicists call the worst prediction in the history of science. Alternative theories propose that dark energy might be a dynamic field that evolves over cosmic time, similar to the field thought to drive cosmic inflation in the early universe. These quintessence models predict that dark energy density and pressure might change, potentially leading to observable effects in precision measurements of cosmic expansion. More exotic possibilities include modifications to gravity itself on cosmic scales. Perhaps Einstein's general relativity breaks down when applied to the entire observable universe, requiring new physics that naturally produces apparent acceleration without invoking dark energy. Testing these alternatives requires measurements of cosmic expansion and structure growth with extraordinary precision across cosmic history. Current observations suggest that cosmic acceleration began approximately 5 to 6 billion years ago, when the universe was roughly half its current age. Before this time, matter density was high enough that gravity dominated cosmic dynamics, causing expansion to decelerate as expected. As the universe expanded and matter density decreased, dark energy eventually became dominant, initiating the acceleration phase we observe today. This transition from deceleration to acceleration represents a fundamental change in cosmic evolution. For the first half of cosmic history, gravity controlled the universe's fate, slowing expansion and enabling the formation of increasingly complex structures. Since acceleration began, dark energy has increasingly dominated, ultimately leading to a future where structure formation ceases and cosmic evolution becomes increasingly simple. Future surveys will measure cosmic acceleration with unprecedented precision across cosmic history. The Dark Energy Survey, Large Synoptic Survey Telescope, and Euclid mission will observe millions of supernovae and map the positions of billions of galaxies, creating four-dimensional maps of cosmic expansion and structure growth. These observations may reveal whether dark energy truly has constant density and pressure, or whether it evolves in ways that could point towards specific theoretical models. They will test whether apparent acceleration could result from modifications to gravity rather than a new form of energy, potentially revolutionizing our understanding of space-time itself. The discovery of cosmic acceleration stands as one of the most important scientific findings of the past century, revealing that our universe is dominated by a mysterious form of energy that we barely understand. This discovery has opened new frontiers in both observational cosmology and fundamental physics, challenging us to understand the true nature of space, time, and energy on the largest scales in the cosmos. Chapter 7. Dark Energy. The Cell. Discovery of cosmic acceleration forced scientists to confront an uncomfortable truth. 68% of everything that exists in the universe consists of something completely unknown to physics. This mysterious component, dubbed dark energy, possesses properties so alien to everyday experience that it challenges fundamental assumptions about the nature of reality. Unlike matter or ordinary energy, dark energy appears to have negative pressure, causing space itself to expand at an accelerating rate. Understanding dark energy requires grappling with concepts that defy human intuition. In ordinary experience, energy and matter have positive pressure. They push outward against their containers. Dark energy behaves in the opposite way, creating what physicists call negative pressure or tension. This negative pressure doesn't pull things together like ordinary tension, but instead drives the accelerating expansion of space itself. The strangest property of dark energy is that its density appears to remain nearly constant as the universe expands. When space grows, the amount of dark energy increases proportionally, maintaining constant density even as the total volume grows. This violates the normal expectation that energy density should decrease as space expands. much like how gas becomes less dense when a container expands. Dr. Sean Carroll, a leading theoretical physicist studying dark energy, explained this bizarre behavior. Dark energy is unlike anything else in physics. If you have a box of ordinary matter or radiation and double the size of the box, the density drops by a factor of 8. But if you have a box of dark energy and double its size, you get twice as much dark energy. It's as if the vacuum itself has energy that gets created as space expands. The simplest theoretical explanation for dark energy is Einstein's cosmological constant, a fundamental property of empty space that creates repulsive gravity. In this interpretation, even completely empty space possesses a baseline energy density that drives cosmic acceleration. The cosmological constant would be truly constant, never changing regardless of how much the universe expands or how much time passes. However, calculating the expected value of the cosmological constant using quantum field theory produces a catastrophic discrepancy. Quantum mechanics predicts that empty space should fluctuate with virtual particles constantly appearing and disappearing. The energy of these fluctuations should contribute to the cosmological constant, but theoretical calculations yield a value 10,120 times larger than observations allow. This enormous disagreement represents what many physicists consider the worst prediction in the history of science. Either our understanding of quantum mechanics is fundamentally flawed, or some unknown mechanism cancels almost all of the vacuum energy, leaving behind the tiny residue we observe as dark energy. Alternative explanations propose that dark energy might not be a property of space itself, but rather a new field or substance that fills the universe. These quintessence models suggest that dark energy could be a dynamic field that evolves over cosmic time, similar to the inflaton field thought to drive cosmic inflation in the early universe. Quintessence fields could have equations of state that change as the universe evolves, potentially leading to observable consequences in precision measurements of cosmic expansion. If dark energy density or pressure evolves over time, the expansion history of the universe would differ from the constant cosmological constant case in ways that future surveys might detect. More exotic possibilities include phantom dark energy, with such extreme negative pressure that it would eventually cause the universe to expand so rapidly that it would tear apart all bound structures, from galaxy clusters down to individual atoms. This Big Rip scenario would occur in a finite time if phantom dark energy density increases as the universe expands. Some theoretical models propose that apparent dark energy could result from modifications to gravity itself on cosmic scales. Perhaps Einstein's general relativity breaks down when applied to the entire observable universe, requiring additional terms or corrections that naturally produce accelerating expansion without invoking mysterious new forms of energy. These modified gravity theories face the challenge of explaining why gravitational effects would change, only on cosmic scales, while remaining consistent with all laboratory and solar system tests of relativity. The modifications must be carefully designed to affect cosmic expansion without disrupting well-tested predictions of our planetary orbits, light deflection, or gravitational waves. Extra-dimensional theories suggest that dark energy could arise from the influence of additional spatial dimensions beyond the familiar 3 dimensions of ordinary space. In these models, gravity might leak into extra dimensions on large scales, creating apparent acceleration without requiring new forms of energy in our 3-dimensional space. Current observations provide some constraints on dark energy properties, but cannot definitively distinguish between different theoretical models. Measurements of cosmic expansion history using supernova cosmic microwave background fluctuations and large-scale structure all point toward dark energy with density close to a cosmological constant, but the precision is not yet sufficient to rule out slowly evolving quintessence fields. The equation of state parameter W which describes the ratio of dark energy pressure to density, appears to be very close to -1 based on current data. A cosmological constant has exactly W equals -1, while quintessence models typically predict W greater than -1, and phantom dark energy would have VIO -1. Future surveys aim to measure W with sufficient precision to distinguish between these possibilities. Dark energy also affects the growth of cosmic structure in ways that could reveal its nature. In a universe dominated by dark energy, gravitational collapse becomes increasingly difficult as acceleration stretches space and opposes structure formation. The rate at which galaxy clusters and other large-scale structures grow depends on both cosmic expansion history and gravitational physics. Comparing measurements of structure growth with predictions from different dark energy models provides complementary tests to expansion measurements alone. If dark energy interacts with matter or modifies gravity, these effects might show up in structure formation, even if they read too subtle to detect in expansion measurements. The Dark Energy Survey spent 6 years mapping 300 million galaxies across cosmic history, measuring both cosmic expansion and structure growth with unprecedented precision. These observations provide some of the strongest constraints on dark energy properties, generally supporting models close to a cosmological constant but leaving room for small deviations. Future surveys will push these measurements to even higher precision. The Large Synoptic Survey Telescope will observe billions of galaxies over 10 years, while the Euclid space mission will map cosmic structure across more than a third of the sky. These surveys may finally determine whether dark energy is truly constant or evolves over cosmic time. Laboratory experiments are also searching for evidence of dark energy through its potential effects on fundamental constants or particle interactions. If dark energy is a field that fills all of space, it might influence the masses or couplings of fundamental particles in ways that could be detected in precision atomic physics experiments. The discovery of gravitational waves has opened new possibilities for probing dark energy. If dark energy affects the propagation of gravitational waves over cosmic distances, these effects might be detectable in observations of black hole mergers or neutron-star collisions by advanced gravitational wave detectors. Theoretical work continues to explore exotic possibilities for dark energy that might emerge from string theory, extra dimensions, or other beyond standard model physics. Some models predict that dark energy could be connected to the hierarchy problem, dark matter, or cosmic inflation, potentially unifying several mysteries in fundamental physics. The ultimate nature of dark energy remains one of the deepest unsolved problems in science. Whether it represents a fundamental property of spacetime, a new field or particle, or a breakdown of our understanding of gravity on cosmic scales, dark energy continues to challenge our comprehension of the universe's most basic properties. Understanding dark energy is crucial for predicting the ultimate fate of the universe and our place within cosmic evolution. If dark energy truly dominates cosmic destiny, the future holds a cold, empty cosmos where galaxies disappear beyond the horizon and stars burn out in isolation. But if dark energy evolves or interacts with other components of the universe, the cosmic future might hold surprises we cannot yet imagine. Chapter 8. Multiple Methods Measuring. The expansion rate of the universe with precision requires multiple independent techniques that can cross-check and validate each other as results. Each method probes cosmic expansion through different physical processes and systematic effects, and the convergence of these diverse approaches provides confidence in our understanding of cosmic dynamics. However, recent measurements using different techniques have revealed puzzling discrepancies that may point toward new physics or unknown systematic errors. The cosmic distance ladder represents the most direct approach to measuring cosmic expansion. This method builds a chain of distance measurements from nearby parallax measurements to distant supernovae, calibrating each step using overlapping distance ranges. The European Space Agency SKEA mission has revolutionized the foundation of this ladder by measuring precise parallax distances to over 1 billion stars, including thousands of Cepheid variables that serve as the next rung. The Hubble Space Telescope has extended Cepheid observations to galaxies hosting Type Ia supernova, providing the crucial calibration link between nearby distance indicators and cosmic expansion probes. The SHOES, Supernova HO for the Equation of State project, led by Adam Rees, has measured Cepheids in 19 supernova host galaxies, achieving distance precision better than 2% for individual objects. These measurements yield a Hubble constant of 73.2 plus or minus 1.3 kilometers per second per megaparsec, representing one of the most precise determinations of cosmic expansion rate ever achieved. The uncertainty includes both statistical errors and systematic effects from Cepheid calibration, supernova standardization, and various observational systematics. Dr. Wendy Friedman, who led earlier Hubble Space Telescope measurements of the Hubble constant, described the power of the distance ladder approach. By building careful calibrations from geometric parallax measurements through Cepheids to supernova, we can trace cosmic expansion from our immediate stellar neighborhood to billions of light-years away. This direct geometric approach provides a robust foundation for measuring how fast the universe expands. But the distance ladder method faces potential systematic errors that could bias the final result. If Cepheid calibrations are affected by metallicity differences between nearby and distant galaxies, or if Type Ia supernova have evolved over cosmic time, these effects could systematically shift the inferred Hubble constant. Extensive studies have found no evidence for such evolution, but the possibility cannot be completely excluded. An entirely different approach uses the cosmic microwave background, the afterglow radiation from the early universe when it first became transparent to light. The Planck satellite measured tiny temperature fluctuations in this radiation with unprecedented precision, revealing the imprint of sound waves that propagated through the primordial plasma. The angular scale of these fluctuations depends on the sound horizon. The distant sound waves could travel before the universe became transparent, combined with the angular diameter distance to the surface of last scattering. By measuring both the physical scale from the known speed of sound and angular scale from observations of the fluctuations, astronomers can determine the expansion history needed to connect these scales. This approach yields h equals 67.4 plus or minus 0.5 kilometers per second per megaparsec when combined with the standard cosmological model. The precision is extraordinary, less than 1%, and the method is completely independent of the distance ladder, relying instead on physics of the early universe and theoretical understanding of cosmic evolution. The tension between these two precise measurements, approximately 9% difference, represents one of the most significant challenges in modern cosmology. Either one or both measurements contain unrecognized systematic errors, or the standard cosmological model requires modification to account for new physics affecting cosmic expansion. Large-scale structure surveys provide a third independent probe of cosmic expansion through baryon acoustic oscillations, the same sound waves detected in the cosmic microwave background, but observed as patterns in galaxy clustering at later cosmic times. As the universe expanded and cooled, these sound waves became frozen into the matter distribution, creating a characteristic scale that serves as a standard ruler for measuring cosmic distances. The Baryon Oscillation Spectroscopic Survey, BOSS, and its successor, EBOSS, have measured the positions and redshifts of over 2 million galaxies, mapping the three-dimensional distribution of matter across a significant fraction of the observable universe. The characteristic scale of clustering features provides distance measurements that, combined with redshift information, determine cosmic expansion rates at different epochs. These measurements generally favor Hubble constant values closer to the Planck result than the distance ladder determination, but with larger uncertainties that cannot definitively resolve the tension. Future surveys, like the Dark Energy Spectroscopic Instrument, DESI, will observe 35 million galaxies over 5 years, potentially measuring baryon acoustic oscillations with sufficient precision to provide definitive tests of cosmic expansion models. Gravitational lensing provides yet another independent approach to cosmic expansion measurements. When massive galaxy clusters bend light from background galaxies, they create multiple images of the same distant object. If the background source varies in brightness over time, the different light paths through the gravitational lens create measurable time delays between the images. These time delays depend on both the mass distribution of the lensing cluster and the angular diameter distances involved, which are sensitive to cosmic expansion rate. The HO-LICAO-W collaboration has measured time delays for several strongly lensed quasars, yielding H equals 73.3 plus or minus 1.7 kilometers per second per megaparsec, in excellent agreement with the distance ladder result. Surface brightness fluctuations in elliptical galaxies offer another distance indicator that bypasses some systematic concerns affecting Cepheids and supernovae. This method measures the pixel-to-pixel brightness variations in galaxy images, which depend on the number of unresolved stars and thus on distance. Recent measurements using this technique support intermediate values of the Hubble constant. The tip of the red giant branch provides an alternative to Cepheids for measuring distances to nearby galaxies. This method uses the consistent brightness of low-mass stars at a specific evolutionary phase, detected as a sharp edge in color magnitude diagrams. Red giant tip measurements generally yield Hubble constant values intermediate between the distance ladder and cosmic microwave background results. Dr. Brad Peterson, who has developed alternative distance measurement techniques, explained the importance of multiple methods. Each approach to measuring cosmic expansion has its own systematic effects and potential biases. Only by using completely independent techniques can we build confidence that we truly understand how fast the universe expands. Recent work has explored whether the Hubble tension could result from local environmental effects rather than global cosmic properties. If we live in a region of space with slightly lower matter density than the cosmic average, local expansion rates could differ from global values inferred from cosmic microwave background observations. However, detailed studies of the local universe find no evidence for significant density variations on scales large enough to affect Hubble constant measurements. The local Hubble flow appears remarkably smooth and isotropic, suggesting that environmental effects cannot explain the observed tension. Alternative explanations for the Hubble tension include new physics in the early universe that would affect cosmic microwave background predictions without changing distance ladder measurements. Additional relativistic particle species, exotic dark matter interactions, or modifications to dark energy properties could potentially reconcile the discrepancy. Future observations will continue to refine all approaches to measuring cosmic expansion. The James Webb Space Telescope will extend Cepheid observations to greater distances and improve calibrations through infrared observations less affected by dust extinction. Next-generation cosmic microwave background experiments will measure polarization and secondary anisotropies with higher precision. The Vera Rubin Observatory will discover thousands of strongly lensed systems suitable for time delay measurements, while improved understanding of gravitational lensing mass models will reduce systematic uncertainties. Advanced simulations of cosmic structure formation will improve theoretical predictions for baryon acoustic oscillations and other expansion probes. The resolution of the Hubble tension may require new physics beyond the current standard model of cosmology, potentially pointing toward discoveries that revolutionize our understanding of cosmic evolution. Alternatively, Subtle systematic effects in one or more measurement techniques may explain the discrepancy without requiring exotic new physics. Regardless of the ultimate resolution, the development of multiple independent methods for measuring cosmic expansion represents one of the great achievements of observational astronomy. These techniques push the boundaries of observational precision while probing fundamental physics across vast scales of space and time, revealing the dynamic nature of the cosmos and our evolving place within it. Chapter 9. Cosmic Tensions in the Precise World of Modern Cosmology. A 9% disagreement between two independent measurements represents a crisis that shakes the foundations of our understanding. The Hubble tension, the persistent discrepancy between expansion rates measured using the cosmic distance ladder versus cosmic microwave background observations, has grown more significant as both measurements have become more precise. This tension suggests either unknown systematic errors in our observations or revolutionary new physics that could transform our understanding of cosmic evolution. The magnitude of this disagreement may seem small in everyday terms, but in cosmology, where measurements routinely achieve precision below 1%, a 9% discrepancy represents a statistical significance exceeding 5 sigma far beyond what could reasonably be attributed to random measurement errors. When independent techniques using completely different physics yield systematically different results with such high precision, something fundamental is likely wrong with our understanding. Dr. Adam Rees, leader of the SHOES Supernova Project, characterized the significance of this tension. We've checked and rechecked our measurements using multiple independent techniques. The discrepancy persists and grows more significant as our precision improves. Either we're missing important systematic effects, or the universe is telling us something profound about physics we don't yet understand. The distance ladder measurement, yielding h equals 73.2 kilometers per second per megaparsec, relies on a chain of calibrated distance indicators extending from geometric parallax measurements to type Ia supernova in distant galaxies. Each link in this chain has been scrutinized for systematic effects that could bias the final result. Studies have found no evidence for evolution in supernova properties, metallicity effects in Cepheid calibrations, or environmental influences that could explain the high Hubble constant value. Meanwhile, the Planck satellite's analysis of cosmic microwave background fluctuations yields h equals 67.4 kilometers per second per megaparsec when combined with the standard lambda CDM cosmological model. This measurement assumes that the universe contains only ordinary matter, dark energy, and radiation as described by well-tested physics, using the fluctuation patterns to infer the expansion history needed to produce the observed angular scales. The cosmic microwave background approach provides an early universe measurement that infers the current expansion rate from observations of the universe when it was only 380,000 years old. In contrast, the distance ladder provides a late universe measurement using objects observed at relatively recent cosmic times. The tension suggests that either our understanding of cosmic evolution between these epochs is incomplete, or systematic errors affect one or both measurements. Several independent observational approaches have attempted to resolve this tension by providing alternative measurements of cosmic expansion. Baryon acoustic oscillations in galaxy clustering surveys generally favor values closer to the Planck result, but with larger uncertainties that cannot definitively discriminate between the competing measurements. Gravitational lensing time delay measurements yield h equals 73.3 kilometers per second per megaparsec, in excellent agreement with the distance ladder result. This agreement is particularly significant because time delay measurements use completely different physics, general, relativistic light propagation through curved spacetime, and are subject to entirely different systematic effects than Cepheid and supernova observations. Surface brightness fluctuations in elliptical galaxies provide yet another independent distance measurement technique, yielding intermediate values around 70 kilometers per second per megaparsec. The tip of the red giant branch method also suggests values intermediate between the distance ladder and cosmic microwave background results, though with larger uncertainties. Dr. Wendy Friedman, who's led efforts to develop alternative distance indicators, explained the puzzle. We now have multiple independent ways to measure cosmic distances, each with different systematic effects. The fact that several techniques yield values around 72 to 73, while others favor 67 to 68, suggests the discrepancy is real rather than arising from a single systematic error. The possibility that local environmental effects could explain the Hubble tension has been extensively investigated. If we live in a region of space with lower than average matter density, local expansion rates could differ from global values inferred from cosmic microwave background observations. However, surveys of galaxy motions within 200 megaparsecs of the Milky Way find no evidence for significant density variations on the scales needed to explain the tension. Theoretical explanations for the Hubble tension generally require new physics beyond the standard cosmological model. Early dark energy, a component that would have been significant in the early universe but became negligible later, could affect cosmic microwave background predictions while leaving distance ladder measurements unchanged. Alternative models propose additional neutrino species, exotic dark matter interactions, or modifications to dark energy properties that could reconcile the discrepancy. However, most such models face challenges in simultaneously explaining the Hubble tension while remaining consistent with other cosmological observations. Some proposals suggest that systematic errors might still explain the tension despite extensive searches. Unknown correlations in Cepheid calibration, subtle evolution in supernova properties, or unrecognized effects in cosmic microwave background analysis could potentially shift one or both measurements toward agreement. The James Webb Space Telescope has begun providing new tests of distance ladder systematics by observing Cepheid variables in the infrared, where dust extinction effects are minimized. Early results confirm Hubble Space Telescope Cepheid measurements, strengthening confidence in distance ladder results and deepening the mystery of the Hubble tension. Future cosmic microwave background experiments will improve early universe constraints by measuring polarization patterns and secondary anisotropies with higher precision. These observations will test whether modifications to standard cosmology in the early universe could explain the Hubble tension without contradicting other successful predictions. Next generation large-scale structure surveys will map cosmic expansion and structure growth across cosmic history with unprecedented precision. The Dark Energy Spectroscopic Instrument, DESI, will measure baryon acoustic oscillations using 35 million galaxies, potentially providing definitive tests of cosmic expansion models. The Vera Rubin Observatory will discover thousands of supernova and gravitational lensing systems, expanding both the distance ladder and time delay measurement samples by orders of magnitude. These observations will test whether the Hubble tension persists as sample sizes grow and systematic uncertainties decrease. Advanced theoretical work continues to explore exotic possibilities for resolving the tension through new physics. Some models propose that dark energy was different in the early universe, while others suggest modifications to gravity or interactions between dark matter and radiation that could affect cosmic expansion history. The resolution of the Hubble tension may require abandoning some cherished assumptions about cosmic evolution. Perhaps the universe underwent phases of evolution not captured by current models. Or maybe fundamental physics operates differently on cosmic scales than in laboratory environments. Alternatively, the tension might reveal subtle systematic effects that have escaped detection despite extensive scrutiny. The history of precision astronomy includes examples where apparent Discrepancies led to important discoveries about instrumental effects or observational biases that have been previously overlooked. Dr. Alicia Verd, a cosmologist studying the Hubble tension, captured both the frustration and excitement of the current situation. The Hubble tension is either telling us that we don't understand our instruments as well as we think, or it's the first hint of new physics beyond the standard model of cosmology. Either discovery would be scientifically important. The Hubble tension has already motivated significant advances in observational techniques and theoretical understanding. The push to achieve higher precision and identify potential systematic effects has improved our understanding of cosmic distance measurements, stellar astrophysics, and early universe physics. Whether the tension ultimately points toward new physics or reveals previously hidden systematic effects, its investigation is driving the next generation of cosmological observations and theoretical developments. The resolution may require observations and techniques not yet developed, continuing the long tradition of cosmic mysteries that push the boundaries of human knowledge and technological capability. The Hubble tension exemplifies how precision measurements in cosmology can reveal unexpected phenomena that challenge our understanding of the universe. As observations become increasingly precise, such tensions may become more common, pointing toward new physics or subtle effects that require revolutionary advances in our understanding of cosmic evolution. Chapter 10. Future Expansion Looking Forward Across Cosmic Time. The accelerating expansion of our universe paints a picture of cosmic evolution that is both fascinating and deeply unsettling. If current observations correctly describe the nature of dark energy, the future holds a cosmos fundamentally different from anything that has existed before, a universe evolving toward maximum entropy, cosmic isolation, and eventual thermodynamic death. Understanding where cosmic expansion is taking us reveals the ultimate context for all of cosmic evolution and our place within it. The current expansion rate of approximately 70 kilometers per second per megaparsec might seem constant from human perspective, but cosmic expansion operates on timescales that dwarf human experience. Over the next several billion years, the accelerating expansion driven by dark energy will gradually reshape the observable universe, carrying distant galaxies beyond our cosmic horizon and fundamentally altering the night sky visible to any future civilizations. In approximately 100 billion years, galaxies beyond our local group will have receded so far that their light can no longer reach us. The observable universe will shrink dramatically, containing only the Milky Way, Andromeda, and a few dozen smaller galaxies bound together by gravity. Future astronomers in this era would see a universe that appears to contain only their local galaxy cluster surrounded by empty space, a cosmic perspective radically different from our current view of a universe filled with billions of galaxies. Dr. Lawrence Krauss, who has studied the far future implications of cosmic acceleration, described this cosmic isolation. Dark energy is gradually erasing the evidence of the Big Bang and cosmic evolution. Future civilizations may have no way to discover that the universe was once dense and hot, or that it contains billions of other galaxies beyond their local group. The cosmic context that seems so obvious to us will be lost forever. The process of cosmic isolation occurs gradually but inexorably. Galaxies currently at distances of 15 to 20 billion light-years are already receding faster than the speed of light due to the expansion of space. Light emitted from these galaxies today will never reach us, even if we wait infinitely long. As expansion accelerates, this cosmic horizon gradually encompasses closer and closer objects. The physics driving this acceleration depends on the nature of dark energy, which remains one of the deepest mysteries in cosmology. If dark energy behaves as a cosmological constant, maintaining constant density as space expands, then acceleration will continue indefinitely, eventually leading to exponential cosmic expansion where the universe doubles in size at regular intervals. In this scenario, The expansion rate approaches a maximum value determined by the dark energy density. Space expands so rapidly that even gravitationally bound systems like galaxy clusters could eventually be torn apart. Over timescales of 1,012 years, the accelerating expansion might overcome the gravitational binding of successively smaller structures, potentially disrupting individual solar systems. More extreme models of phantom dark energy predict even more dramatic future evolution. If dark energy density increases as the universe expands, acceleration could become so intense that it would tear apart atoms themselves in a finite time. This Big Rip scenario would end the universe in a cataclysmic expansion event occurring perhaps 20 to 30 billion years from now. Current observations cannot definitively distinguish between these possibilities. The equation of state parameter W that characterizes dark energy pressure appears to be very close to -1, the cosmological constant value, but measurements are not yet precise enough to rule out slowly evolving phantom dark energy that could lead to a big rip. Future surveys will measure cosmic expansion history with unprecedented precision across cosmic time. The Dark Energy Survey, Large Synoptic Survey Telescope, and Euclid mission will observe millions of supernovae and map billions of galaxies, potentially determining whether dark energy density and pressure evolve in ways that could alter the cosmic future. These observations may reveal that dark energy is not truly constant, but evolves according to quantum field dynamics similar to cosmic inflation. If dark energy weakens over time, cosmic acceleration could eventually cease, potentially allowing gravity to regain dominance and alter the universe's ultimate fate. Even if acceleration continues indefinitely, the cosmic future includes epochs of evolution unlike anything in the universe's past. Stars will continue forming from remaining gas supplies for approximately 100 trillion years, but stellar birth rates will decline exponentially as galaxies exhaust their fuel and merger rates decrease. Due to cosmic expansion, red dwarf stars with lifetimes exceeding 10 trillion years will become the dominant stellar population as more massive stars exhaust their nuclear fuel. Eventually, even these long-lived stars will burn out, leaving behind white dwarf remnants, neutron stars, and black holes as the only surviving compact objects. The era of stellar evolution will give way to the degenerate era, dominated by the slow evolution of stellar remnants. White dwarfs will gradually cool over periods of 1,015 years, eventually becoming cold black dwarf stars invisible against the cosmic background. Brown dwarfs and free-floating planets will continue orbiting through empty space, occasionally undergoing gravitational encounters that alter their trajectories. Proton decay, if it occurs as predicted by some theories beyond the standard model, would eventually disintegrate all remaining atomic matter over timescales of 1,034 years. Even the most stable atomic nuclei would spontaneously decay, reducing planets, brown dwarfs, and stellar remnants to elementary particles and radiation. Black holes would become the dominant remaining structures in this far future universe. These gravitational monsters, from stellar mass remnants to supermassive behemoths like Sagittarius asterisk, would slowly evaporate through Hawking radiation over periods so vast that they challenge comprehension. A black hole with the mass of the Sun would take 1,067 years to evaporate completely. Thus, time span 1,057 times longer than the carnage of the universe. The most massive black holes, containing billions of solar masses, would persist for periods exceeding 10,100 years, before finally disappearing in bursts of elementary particles and radiation. During their final moments, these evaporating black holes would briefly become the most luminous objects in an otherwise cold and empty cosmos. Dr. Freeman Dyson, who pioneered studies of far future cosmic evolution, captured the immensity of these timescales, the difference between the current age of the universe and the black Whole evaporation timescale is like comparing a single second to a time longer than the age of the universe, multiplied by itself billions of times. We're contemplating a future so vast that all of recorded human history represents an infinitesimal moment. Even after all matter has decayed and all black holes have evaporated, quantum fluctuations might occasionally create structures in the vacuum of space. Over periods of 101,050 years or longer, thermal fluctuations could spontaneously assemble collections of particles that briefly recapitulate complex structures, perhaps even conscious observers, before dissipating back into randomness. The ultimate fate depends on whether the universe continues expanding forever or undergoes more exotic evolution. Some speculative scenarios propose that vacuum decay could alter the fundamental properties of space and time, potentially creating new physics that would completely transform cosmic evolution. Alternative cosmological models suggest that cosmic expansion might not continue indefinitely. Cyclic universe theories propose that expansion could eventually reverse, leading to a big crunch that would compress all matter and energy back into an extremely dense state, possibly followed by a new Big Bang. However, current observations provide no evidence for such cyclical behavior. Dark energy appears to be winning its competition with gravity, driving toward a future of continued expansion and cosmic isolation rather than eventual collapse and renewal. The contemplation of cosmic futures reveals the temporary nature of all structures in the universe, from galaxies and stars to planets and life itself. Yet this cosmic perspective also highlights the remarkable emergence of complexity and consciousness during the brief cosmic moment when physical conditions allow such phenomena to exist. Understanding the future of cosmic expansion provides crucial context for evaluating humanity's place in cosmic evolution. We exist during a unique epoch when galaxies are clearly visible across vast distances, when stars actively form complex elements, and when planetary systems can maintain stable conditions for billions of years. This cosmic context suggests that consciousness and intelligence may be rare and precious phenomena that exist only during brief windows of cosmic evolution. The far future of an expanding universe may be fundamentally incompatible with the emergence and persistence of complex structures capable of contemplating their own existence. Chapter 11. Ultimate speed. As we reach the culmination of our exploration into cosmic expansion, we confront the ultimate question: what is the maximum speed at which the universe can expand? And what happens when space itself grows faster than light can travel through it? The answer reveals not just the mechanics of cosmic growth, but fundamental limits on causality, observation, and the very structure of space-time that govern the evolution of everything that exists. The speed of cosmic expansion operates according to principles that shatter human intuition about motion and velocity. Unlike objects moving through space, which are limited by Einstein's cosmic speed limit of light, space itself has no such restriction. The expansion of the universe can and does carry distant objects away from us faster than light speed without violating any law of physics, because the objects aren't actually moving through space at superluminal velocities. Currently, galaxies at distances greater than approximately 14 billion light-years are receding from us faster than the speed of light due to cosmic expansion. This doesn't mean these galaxies are racing through space at 300,000 kilometers per second. Rather, space itself is expanding fast enough that the cumulative growth over such vast distances exceeds light speed. It's like being on an extremely long conveyor belt, moving faster than you can run. You're not running faster than your maximum speed, but the belt carries you at velocities exceeding your individual capabilities. Dr. Tamara Davis, who studies cosmic horizons and expansion, explained this counterintuitive physics. When we say distant galaxies recede faster than light, we're not talking about motion through space. We're talking about how much space grows between us and them per unit time. Space can expand at any rate without violating relativity, because nothing is actually moving through space faster than light. This superluminal recession creates what cosmologists call the Hubble sphere, a boundary at approximately 14 billion light-years distance beyond which objects recede faster than light speed. This boundary moves outward over time as the Hubble constant decreases, but its existence at any given moment fundamentally limits what we can potentially observe about the universe. The physics becomes even more profound when considering the particle horizon, the boundary of our observable universe determined by the distance light has traveled since the Big Bang. Due to cosmic expansion, this observable horizon currently extends about 46.5 billion light-years in every direction, encompassing galaxies whose light has been traveling toward us for nearly the entire age of the universe. Objects near the particle horizon appear to us as they existed when the universe was very young, because their light has taken most of cosmic history to reach us. The most distant observable galaxies show us cosmic conditions when the universe was less than 500 million years old, providing direct observational access to cosmic evolution across 13 billion years of expansion. But here's where the ultimate speed limits become terrifying and beautiful. There exists an event horizon beyond which we will never receive information, no matter how long we wait. This cosmic event horizon, currently located about 16 billion light-years away, marks the boundary beyond which light emitted today will never reach us due to accelerating cosmic expansion. If cosmic acceleration continues as observations suggest, this event horizon will gradually move inward, encompassing more and more of the currently observable universe. Galaxies beyond this boundary become causally disconnected from us. No signal, influence, or information of any kind can travel from these regions to our location, even given infinite time. The ultimate expansion speed depends critically on the nature of dark energy driving cosmic acceleration. If dark energy behaves as Einstein's cosmological constant, maintaining constant density as space expands, then the expansion rate will asymptotically approach a maximum value determined by the dark energy density. In this scenario, cosmic expansion eventually becomes exponential, with the universe doubling in size at regular intervals. The characteristic timescale for this doubling, called the de Sitter time, is approximately 10 billion years based on current dark energy density measurements. This means the universe will be twice as large 10 billion years from now, 4 times as large after 20 billion years, and so on indefinitely. During exponential expansion, the observable universe gradually shrinks as more and more galaxies cross beyond our cosmic event horizon. Eventually, only gravitationally bound objects within our local group would remain visible, creating a profoundly isolated cosmic perspective for any surviving civilizations. More extreme possibilities arise if dark energy evolves over time rather than remaining constant. Phantom dark energy with equation of state W-1 would create expansion rates that increase without limit, potentially leading to infinite expansion velocities in finite time. Such scenarios predict a big rip where space expands so rapidly that it tears apart all bound structures, from galaxy clusters down to individual atoms. Current observations cannot definitively distinguish between these possibilities. The dark energy equation of state parameter appears very close to W equals -1 based on supernova, cosmic microwave background, and large-scale structure measurements. But the precision is not yet sufficient to rule out slowly evolving phantom dark energy. Future surveys will measure cosmic expansion history across billions of years with unprecedented precision. The Vera Rubin Observatory will discover 100,000 Type Ia supernova over its 10-year operation, while the Euclid space mission will map cosmic structure across more than a third of the sky. These observations may finally determine whether dark energy is truly constant or evolves in ways that could alter the universe's ultimate expansion rate. The concept of ultimate expansion speed also connects to fundamental questions about the nature of spacetime itself. In Einstein's general relativity, space and time are unified as a single four-dimensional continuum that can be curved, twisted, and stretched by matter and energy. Cosmic expansion represents the stretching of this spacetime fabric on the largest scales. Quantum theories of gravity suggest that spacetime itself might have fundamental limits or discrete structure at the smallest scales. If space consists of discrete units, quantum foam, or string theoretic structures, then there might be fundamental limits to how rapidly space can expand, similar to how sound waves cannot propagate faster than the speed of sound in a material medium. However, such quantum gravitational effects would only become important at expansion rates vastly exceeding anything predicted by dark energy models. The Planck scale, where quantum gravity effects become significant, involves energies 1,016 times higher than those associated with current cosmic acceleration. Some speculative theories propose that cosmic expansion could encounter fundamental barriers that would halt or modify acceleration. If dark energy represents a quantum field, similar to the inflaton that drove cosmic inflation, it might eventually undergo phase transitions that would dramatically alter expansion dynamics. Alternative scenarios suggest that cosmic expansion might not continue indefinitely. Some models predict that dark energy could decay or transform into ordinary matter and radiation, eventually allowing gravity to regain dominance and possibly reverse cosmic expansion into a big crunch. The study of cosmic expansion also reveals deep connections between local physics and global cosmic structure. The expansion rate affects fundamental constants, particle masses, and physical processes in ways that might be detectable in precision laboratory experiments. Future tests of fundamental physics may reveal signatures of cosmic acceleration in atomic spectra, gravitational wave propagation, or other measurable phenomena. Understanding ultimate expansion speeds has profound implications for the possibility of interstellar or intergalactic travel. Even if hypothetical civilizations could approach light speed, cosmic expansion would prevent them from reaching galaxies beyond a certain distance. The expansion of space creates an effective prison that confines all possible communication and travel to an ever-shrinking region of the cosmos. This cosmic isolation also affects the long-term prospects for energy and information processing. Advanced civilizations would find their available resources limited to gravitationally bound systems within their local cosmic neighborhood, ultimately constraining the complexity and duration of any possible computational processes. Dr. Max Tegmark, who has studied the cosmological implications for advanced civilizations, noted, "Cosmic acceleration creates fundamental limits on what any civilization can achieve. Even with unlimited time and perfect technology, you cannot travel to distant galaxies or access their resources. The universe is becoming less connected rather than more connected as time passes. The ultimate speed of cosmic expansion represents more than an abstract physical limit. It defines the boundaries within which all cosmic evolution must occur. Understanding these boundaries provides crucial context for evaluating humanity's place in cosmic history and the ultimate constraints on the development of complexity and consciousness in an expanding universe. As we contemplate the maximum rate at which space itself can grow, we confront the fundamental architecture of reality and the cosmic context that shapes all possible futures for matter, energy, life, and consciousness in our expanding cosmos. Throughout this extraordinary journey across cosmic scales and through billions of years of universal evolution, we've uncovered one of the most profound truths about reality. Space itself grows at a rate of 70 kilometers per second for every megaparsec of distance, carrying galaxies away from us in a cosmic exodus that began 13.8 billion years ago and continues to accelerate with each passing moment. But perhaps the most remarkable revelation isn't the speed itself. It's what this expansion means for our understanding of cosmic destiny and our place within the grand architecture of space-time. We began with the simple observation that distant galaxies appear redder than they should. And we've arrived at a universe dominated by mysterious dark energy that pushes space apart with increasing intensity. We've discovered that 68% of everything that exists consists of something we don't understand, driving our cosmos toward a future of cosmic isolation and thermodynamic death that challenges every assumption about permanence and meaning. Yet, in comprehending these cosmic truths, we've also revealed something extraordinary about human capability and scientific achievement. The measurement of cosmic expansion represents perhaps the most ambitious observational program in human history, extending from parallax measurements of nearby stars to observations of galaxies billions of light years away. We've learned to use dying stars as cosmic lighthouses, to trace sound waves from the birth of the universe, and to measure the stretching of space-time itself through gravitational wave detection. As you return to your daily existence after this cosmic perspective, carry with you the knowledge of your true situation in space and time. The ground beneath your feet participates in cosmic expansion on scales so vast that local gravitational effects completely dominate. Your body contains atoms forged in stellar cores, whose formation was governed by cosmic expansion rates in the early universe. Every breath connects you to chemical elements dispersed by cosmic processes operating across billions of years of universal evolution. When you look up at distant galaxies through a telescope, remember that you're seeing them as they appeared billions of years ago, when space was smaller and cosmic conditions were dramatically different from today. The light reaching your eyes has been stretched by cosmic expansion, redshifted by space itself, growing during the photon's journey across the cosmos. You're directly observing the dynamic nature of space-time through the color changes of ancient starlight. Consider the profound implications of living in an accelerating universe. Future civilizations billions of years from now will inhabit a cosmos where most evidence of the Big Bang and cosmic evolution has disappeared beyond their observable horizon. They may never discover that space expands, that the universe had a beginning, or that countless galaxies exist beyond their local cosmic neighborhood. We live during a unique cosmic epoch when the evidence for universal expansion remains clearly visible. The Hubble tension, the puzzling disagreement between different measurements of cosmic expansion, reminds us that our understanding remains incomplete. This discrepancy may point toward new physics that revolutionizes cosmology, or it may reveal subtle systematic effects that have escaped detection despite decades of careful analysis. Either discovery would represent a triumph of observational precision and scientific methodology. The far future painted by cosmic acceleration appears bleak from human perspective, a universe evolving toward maximum entropy, where stars burn out, galaxies separate, and consciousness becomes impossible. Yet this cosmic context also reveals the extraordinary improbability and preciousness of our current situation. We exist during the brief cosmic moment when expansion allows complexity to emerge while keeping the universe's history visible to scientific investigation. You are not separate from cosmic expansion, but intimately connected to it through every physical process that sustains your existence. The formation of atomic nuclei in the early universe occurred at expansion rates that determined which elements could form and in what abundances. The cooling that allowed atoms to assemble happened according to expansion timescales that governed the universe's thermal evolution. Star formation, galaxy evolution, and planetary system development all proceed according to cosmic expansion rates that set the timescales for cosmic structure formation. The mystery of dark energy reminds us how much we still don't know about the fundamental nature of reality. Despite remarkable progress in measuring cosmic expansion with precision below 1%, we remain ignorant about the physical mechanisms driving acceleration. Whether dark energy represents vacuum fluctuations, new fundamental fields, or modifications to gravity on cosmic scales remains an open question that may require revolutionary advances in theoretical physics. Future observations will continue pushing the boundaries of cosmic expansion measurements. Next-generation surveys will discover millions of supernovae, map billions of galaxies, and measure gravitational waves from cosmic sources, potentially resolving current tensions and revealing new aspects of cosmic acceleration. These observations may confirm that our universe is truly dominated by mysterious dark energy, or they may reveal surprises that transform our understanding of cosmic evolution. The speed of cosmic expansion, 70 kilometers per second per megaparsec, represents more than a number describing how fast space grows. It encodes fundamental information about the composition, age, and ultimate fate of everything that exists. This single measurement connects the smallest quantum fluctuations that seeded cosmic structure to the largest scale evolution of spacetime itself. Perhaps most remarkably, understanding cosmic expansion has revealed that consciousness and scientific investigation occupy a privileged position in cosmic evolution. Only during the current cosmic epoch do physical conditions allow complex structures to form while maintaining access to the phone epoch do physical conditions allow complex structures to form while maintaining access to the observational evidence needed to understand cosmic history and destiny. The measurement of universal expansion stands as one of humanity's greatest intellectual achievements, revealing our true cosmic context while demonstrating the power of scientific methodology to uncover nature's deepest secrets. From Edwin Hubble's pioneering observations to modern space-based surveys, each generation has refined our understanding of how fast space grows and what this growth means for cosmic evolution. If you followed this journey through the expanding cosmos, subscribe and give this video a thumbs up. Explore my investigation of dark energy's mysterious nature in the force that's tearing the universe apart. You'll discover even more profound mysteries about cosmic acceleration. The next time cosmic expansion carries a distant galaxy 1 meter farther away, which happens roughly every million years, remember that you've witnessed the fundamental process that shapes all of cosmic evolution, driving our universe from its dense beginning toward its uncertain but inevitable future in the vast, cold, expanding darkness of space.